So, in today's lesson, it is going to be an extension of the periodic trends section, and also we're going to talk about valence electrons. So, the periodic trends are considered to be a general trend when we memorize it. And so, let's review those periodic trends real quick and then get into the actual lesson. And so, the first trend is atomic radius. And it is decrease, decrease. The other trends, so ionization energy, electron affinity, which, like I said, very rarely do we hear questions about, or electronegativity, which is the one that we talk most about because it's the one that's about chemical bonding. They are going to be increase up, increase across. That's what we call as our general trend. But there are exceptions. Not all elements are going to decrease in atomic radius across. Not all elements are going to increase in electronegativity across. And so, especially in the F block, with your F block elements, they do some really strange stuff. So when we memorize these trends, these are what we call the general trend, but there are exceptions. AP only expects you to understand a couple of the exceptions, and you're only going to see a couple questions based on these exceptions. So this first graph is a graph of ionization energy versus your atomic number. And the reason I want you to see this is because I need you to understand the general trend, but also those weird exceptions. So if you notice at the top, this is not just a normal graph where it's just a linear positive slope graph or it's quadratic or whatever. Like it's not a normal graph because I have these peaks and then it drops and then it peaks and then it drops and then it peaks and then it drops. It just keeps doing that process over and over and over. Well, if we look here at what's peaking, it is our noble gases. Once something has the electron configuration of a noble gas, it is stable and it does not want to change. So the noble gas in the beginning definitely does not want to change. Remember, ionization energy is the energy required to remove one electron. They don't want to lose electrons. They're perfectly stable. So it takes, in comparison to the other things in their period, it takes the most energy. So between hydrogen and helium, helium has more. And for your second period, between lithium up to neon, neon's the most. Third period, sodium up to argon, argon's the most. Fourth period, potassium up to krypton, krypton's the most. And then once we get to the sixth period, rubidium up to xenon, xenon's the most. But you'll notice that there's some weird drops in some of these places, and it doesn't necessarily follow just a perfect, so like helium, hydrogen to helium was just a perfect positive linear line, but these aren't. And so let's talk about why. If we look at the actual ionization energy values, so there are periodic tables that have these values on them. AP will not give you those for the AP exam. So I do not want us to ever rely on these graphs that have the actual numbers because you will not see them on the AP exam. We just need to know the general trend. If you memorize the trend, then you are okay with everything else. So the trend for ionization energy is increase up and increase across. And if I look, for the most part, that's true. Increase up, increase up, increase up, increase across, increase across. But then some weird stuff happens, especially over here. So this one doesn't even show us the D block. The D block has a lot more that do weird things. But you'll notice that in these two columns, there's some exceptions. So this number, it increases up, but then it drops and then increases again. It increases up and then it drops a little bit and then increases again. Increases up, drops a little bit and increases again. But the biggest drop is here between your nitrogen and oxygen. And so AP is going to expect you to be able to explain why is there a slight change to that increase up between this group and this group. Most of the time, the question is going to be between phosphorus and sulfur, but it could be any of these. So let's look at the next slide and talk about it. Stability in the p and the d orbitals comes from being half full. So they actually want to be at that MP3. So N, remember, is just a generic energy level. So like 2P3, 3P3, those sort of things. So they like to be at the NP3. They don't really want to be at NP4. If you look back here, I'll just write it up above. So this is P1, P2, P3, P4, P5, P6. This would be the 2s, the 3s, the 4s, yada yada. So if we look at it, it takes more energy to remove the P3 than it does in general for the P4. Now, when we start getting down here, some weird stuff starts happening because of the D and the F blocks. So we're really going to mainly look at these first two periods. And what's happening is it is happy at the P3. So it really doesn't want to lose it, but it's unhappy at the P4 because it can lose one more and get to the P3. And so the same thing is true when we talk about ND6 or ND5, because remember, in p orbitals, half full would be 3. In d orbitals, half full would be 5. And so the same thing is true there if you look at those trends for the ND6 and the ND5. So I want us to draw the orbital diagram for nitrogen and oxygen and then talk about what's happening there. And so remember, orbital diagrams are where we are going to draw the line to represent the orientation. So for nitrogen, we're going to start out with 1s2. Going to raise it up a little bit to the 2s, so then it's going to be 2s2. I should have done this a little bit lower. I'm going to raise it up just a little bit more. And nitrogen is going to be 2p3. So I go 1, 2, 3. If I look back at this value here, it tells me nitrogen is 1402. And this is going to be ionization energy is in kilojoules per mole. So this one is nitrogen. If I come down here to do oxygen, I'm going to go 1s, 2s. But oxygen's 2p has, whoopsie, that didn't work. No. So oxygen is going to be 2p4. So we're going to go 1, 2, 3, 4. And this fourth one annoys oxygen, and it sort of wants to get rid of it because these orbitals like just to have one in them. So they like to be half full or all the way full, and they have to deal with what they have. But because of that, it makes oxygen drop down to 1314 kilojoules per mole, which is slightly lower and does not follow that perfect trend. So it is not always that perfect increase up. Again, the questions for these two is almost always going to be about phosphorus and sulfur. And I know this change is minimal. It is a very small amount of change of kilojoules. Kilojoules is a pretty large amount of energy. And so it's more significant than it looks like if we're just looking at the base value of 1060 to 1005. But just realize it is because it likes to be at P3. It sort of annoys it to be at P4. It wants to be half full or all the way full. And to get to the all the way full for the things that aren't stable, that's why they lose or gain electrons. So valence electrons are really based mostly on the electron configuration. If I give you the electron configuration, you can look at the outermost s and p orbitals. I did that the other day when we were doing electron configuration to figure out the number of valence electrons. Groups 1 and 2 and 13 through 18 have set charges, and so they have a certain number of valence electrons. Group 14 has a couple elements, tin and lead, that have variable charges. They have multiple charges, and so they're a little bit of an exception. Your transition metals have variable charges with the exception of silver and zinc. You guys do need to remember those things you had to memorize in your high school level chemistry classes. Even though silver and zinc are in a transition metal, they have a set charge. Silver is always a positive one. Zinc is always a positive 2. And then even though tin and lead are not a transition metal, they're in group 14, they can take on either a positive 2 or a positive 4 on their charges. So group 1 are your alkali metals, and all of group 1 elements, including hydrogen, which is not an alkali metal but is there because of the valence electrons. They all have just one valence electron. Group 2 has 2 valence electrons. They're called your alkaline earth metals. Group 17 are your halogens, and they have 7 valence electrons. And group 18 are your noble gases. They have 8 valence electrons because they would have a full s and p orbital. The exception is helium because it only has 2 valence electrons. So which of the following represents an electron configuration that corresponds to the valence electrons of an element for which there is an especially large jump between second and third ionization energies? So these are going to be problems where you have to think about what is happening to the electron configuration and what it means by this really big jump. And so when we're talking about ionization energies, we are meaning how many electrons have they lost. So ionization energy number 1 means it lost 1 electron. Number 2 means it lost 2. 3 means it lost third. So if it has 3 ionization energies, it has lost 3 electrons. Again, N is the energy level, which is your principal quantum number. When we're talking about the actual names of the quantum numbers, which AP doesn't expect you to know that, but they do expect you to be comfortable with electron configuration. So let's go back and talk about what it's really referring to. It is meaning in these things, so this is all ionization energy 1. So it's saying that there's a huge jump from the element losing its second electron to its third electron. So if we look at this and don't really look at the numbers, but what we're saying is, let's say we're looking at the third row. Sodium wants to lose its first electron. It only has 1 valence electron. It wants to get rid of it. It's going to give it away to something else to become stable. When it loses its 1 electron, sodium takes on the electron configuration of neon. It is now stable, and its electron configuration is going to be 2p2 and then 2s2, 2p6 to be able to be stable. Magnesium would want to lose 2 electrons. So it would lose 1 electron from its energy level, another electron from its energy level, and if it lost both of them, then it would also become neon. So it wants to lose 1, 2 to become that. It does not want to lose another one because then that makes it not be the electron configuration of a noble gas. That's what this question is asking. Is it saying there's an especially large jump between the second and third ionization energies? So it's saying what would be the electron configuration that would match that? Well, its valence electrons would be 2 because it wants to lose 2 electrons. It does not want to lose a third electron. That's why it's saying between second and third ionization energies. And so this is talking about your alkaline earth metals. It is talking about anything in this group because it would lose 1 electron, 2 electron to become these noble gases. It does not want to lose any more than that. And so the correct answer is going to be NS2 because it's going to lose 2 of its s electrons and become a noble gas and be happy. It does not want to lose its third electron. So if sodium reacts to chlorine to form NaCl, which of the following elements reacts with sodium to form an ionic compound in a 1-to-1 ratio and why? So really quick, we need to understand what forms an ionic compound. And an ionic compound is going to be a bond between the cation and an anion. Remember, cation we said was positive in our last lesson. Anion is negative. So that is what forms an ionic compound, first of all. Sodium is a positive 1. Chlorine is a negative 1. It's saying sodium is going to bond with something else again in a 1-to-1 ratio. And why? So will sodium bond with potassium? Well, no, because potassium is a positive 1, and 2 positives do not make an ionic compound, so that's a no. Magnesium. Well, magnesium is a positive 2 because it's in group 2. This one's in group 1. This one's in group 2. So that's also a no because it has the same positive charge. It needs to be one positive thing, one negative thing. Argon. And again, these two that are talking about mass, like I said, that's usually, I can't think of a single thing in chemistry that we relate back to its mass. It is all the other characteristics, not the mass that we use to decide what the property is going to be. Well, first of all, argon has a charge of 0 because it has a stable number of electrons. It has 8. It doesn't want to lose any, and so that's not going to bond. Bromine is a negative 1, and it's because it has the same number of valence electrons as chlorine, so this one is going to be correct. If you have forgotten these charges, that is something you probably want to go back and review. So because group 1 has 1 valence electron, it becomes positive 1. Because group 2 has 2, it becomes a positive 2. Group 13 is going to be a positive 3. Group 14, we say it's a positive or a negative 4 or a positive 2, but I really hate using all that information without knowing more about it. So carbon, silicon, and germanium are all either nonmetals or metalloids. And so because of that, these three, if they are going to bond ionically, they're going to become negative, but they almost never bond ionically. They almost always bond covalently. Tin and lead are metals, so they are going to be the ones that take on that positive 2 or that positive 4 charge. These up here really are going to be the negative 4, but again, that's really almost never happens with that, just because they bond covalently. This group is going to be a negative 3. This group is a negative 2. This group is a negative 1. And these are 0 because they're not going to bond. So I would recommend printing out a periodic table and labeling the periodic table. You may even want to go through and label the valence electrons. Just realize by the end of the year, we cannot have any extra information on our periodic table. AP gives you a blank periodic table. So by the end of the year, we want to have this stuff stuck in your head. Last question. All the chlorides of the alkaline earth metals have similar empirical formulas. And we've talked about empirical formulas in a previous lesson, as shown in the table above. Which of the following best helps explain this observation? So in this, all of these are formed between, this is a metal, and then chlorine is a nonmetal. So in these, you have a cation and an anion. All of them are chlorine, so chlorine is a negative 1 because it's in group 17. And all of them are group 2 metals, so they're all a positive 2. So this says the correct answer is A, because chlorine gas reacts with metals atoms to form strong double covalent bonds. Well, first of all, these are not covalent. These are all ionic because it's a cation and an anion. So that's not true. Chlorine has a much greater electronegativity than any of the other alkaline earth metals. And that is true because electronegativity is increase up, increase across. But that doesn't explain why they're bonding this way with the alkaline metals. And this is the 2 valence electrons of the alkaline earth metal atoms are relatively easy to remove, and that is going to be the truth of it because of the fact that they have 2 is why they have a positive 2 charge. And on any of these, I'll use beryllium as example. If I have beryllium positive 2 and chlorine negative 1, it takes 2 chlorines to cancel the charge of positive 2. And so that's where we get the BeCl2 or MgCl2 or CaCl2 and so on and so forth. So when they're talking about valence electrons, you can either look at it from where they're at on the periodic table, how many valence electrons they have, but sometimes it relates back to our charges of how many electrons can they lose or can they gain. Remember, these positive cations have lost electrons. These negative anions have gained electrons. And your noble gases do neither because they are already stable.